And we're back again. Hi, everyone. We are going to look at now chapter 2.6. We're skipping 2.5. Right now, I don't really remember what it was and why that was the case, but we're skipping chapter 2.5, so don't be alarmed. If you want to go study it on your own, please feel free. That'd be fun. But we're not going to cover it in class at all. Won't be on any tests or anything. But we're going to look at chapter 2.6, which is graphs of rational functions. And so what we're going to look at is graphs of functions, and you're going to find horizontal and vertical asymptotes, as well as describing the transformations that were done to the function in order to give the look that it has there. Okay? So you remember back in chapter 1.6, we did transformations. And when you're doing the homework for this section, it wouldn't suck if you had those transformations written down somewhere. I recently went and put in graphical transformations into Google, and under the Google images, I found a whole bunch of charts that list all the graphical transformations. Some of them are described a little different than how the textbook does it. But you can easily go there and print one up and see, and there you go. That's kind of not helpful, but I went through and let's see if I can do it. No, maybe I can't. It's the, anyways. So I printed this up, and it's easy to find the graphical transformations. And so if you want to find those, just go get them. Okay. But let's go ahead and start. First of all, where's my stylus? There it is. We need to remember asymptotes. And an asymptote, so if I have f of x equals 1 over x, the graph of this, oops, let's see, as x gets really, really big, when I divide by a really big number, and then I divide by an even bigger number, this gets small, and it gets even smaller. As x gets really, 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 really big, y gets really small. And out to infinity, it starts approaching 0. Never touches 0, but it gets there. And if I divide by a small number, the fraction actually gets bigger. And if I do a really small number, a smaller number, this thing gets even bigger and bigger and bigger and bigger. So as I approach 0, the function starts to spike to infinity. So it goes like that. And when it's negative, when x is negative, y is going to be negative. So it's going to be like that. And this function approaches 0 when x gets really big, and it approaches positive and minus infinity when we approach the origin. Okay? These are the asymptotes. You normally show an asymptote with a dotted line. Kind of hard to do it when they're right on the axes, right? And the vertical asymptotes, occur when we divide by 0. Okay? So when we're testing this, let's see what that was. When we're testing for vertical asymptotes, we just take the denominator and set it equal to 0. In this case, x equals 0. That's where the vertical asymptote is. And so I see a dotted line. Let me do it in blood red. There we go. So here's our vertical asymptote, right at x equals 0. Now for horizontal asymptote, there's a process. Let's say I wanted to know what the, let's see, 2x squared plus 3x minus 9 over x squared plus 1. Nope. X squared minus 4. How's that? And I want to know where are the vertical and horizontal asymptotes. And we'll do the verticals first because those tend to be easier. So for vertical, I take the denominator and set it equal to 0. So x squared, the 4 goes to the other side, take a square root. X is plus or minus 2. There's 2 ways to get a vertical asymptote for this ugly function here. Okay? So that would be the first answer to it. Where are the vertical asymptotes? The vertical asymptotes are at x equals plus or minus 2. And you get it by taking the denominator and setting it equal to 0. Okay? That's always the process for vertical asymptotes. For horizontal asymptotes, there is a process. Step 1, divide by biggest power of x. So that means I'm going to take every term that I have and I'm going to divide it by x squared, because x squared is the biggest term. So I'm going to write this as 2, and then this is x squared over x squared plus 3x over x squared minus 9 over x squared divided by x squared over x squared minus 4 over x squared. Okay, step 2, simplify and reduce. So, well, I can see x squared over x squared is 1. X over x squared will give me 3 over x, and I can't do anything to this. X squared over x squared is 1 minus 4 over x squared. Now, horizontal asymptotes, as you see up here, happen when we're going way out along the x-axis, when x is heading towards 0 or towards infinity. So the way we will frequently represent this as, let me get rid of that. When we're calculating the horizontal asymptotes, we write, what's the limit as x approaches infinity for my function? 2x squared plus 3x minus 9 over x squared minus 4. And what this means here, the limit as x approaches infinity, it means what's the value of this thing as x heads out to infinity. Okay? You know, I know it's not going to touch, but it's going to get really close. And what's the value that it's going to approach? So over here, my step 3 is plug in infinity. Oops. There we go. That's step 3. So I'm going to take my function and plug in infinity. 2 plus 3 over infinity minus 9 over, can I move that? There we go. Infinity squared, holy moly, over 1 minus 4 over infinity squared. Okay, now step 4, get rid of zeros. And that means when I look over here, 3 over infinity, 3 over a hugely huge number is going to be 0. This is going to be equal to 0. 9 over infinity squared, definitely 0. 4 over infinity squared, 0. So what we end up with is 2, 0, 0, 0 over 1. So the limit we just found, the limit as x approaches infinity for this thing comes out to be 2. Because I plugged in the biggest power of x, doop-de-doop-de-doop-de-doop, and then I simplified and canceled stuff out, cancel. Then I got rid of the zeros, 0, 0, 0, and I ended up with 2. So this tells me this function, not this one, this function, when I get out to infinity, it's going to approach 2. What about negative infinity? What if I plug in negative infinity in here? It doesn't really matter. Still going to be 2. So this is my horizontal asymptote. And the process for horizontal asymptote is always the same. You divide by the biggest power of x, you simplify and reduce, you plug in infinity, and then you get rid of the zeros. If you do those 4 steps, you'll always end up with something over here. Now, let's say the something you end up with let's say our function was really not squared, but cubed, okay? Then let's divide by the biggest power of x. Now the biggest power of x, I'll put it there, is x cubed. So I divide by the biggest power of x, 2x cubed over x cubed plus 3x over x cubed minus 9 over x cubed all over x squared over x cubed minus 4 over x cubed. Then what do we do after we divide by the biggest power? Oh yeah, we simplify. Okay, so that'll be 1. And that's going to be 3 over x squared, and x will cancel from the x in the bottom. And this is going to be 9 over x cubed all over x squared over x cubed is 1 over x minus 4 over x cubed. Now what do we do? Oh, plug in infinity. Okay, so this will be, I'm running out of room. All right, I got to get rid of this thing. Sorry, I really wanted to use that graph, but it's going to have to go. So now I'll plug in infinity. So if I go up here, I'm going to get 2 plus 3 over infinity squared minus 9 over infinity cubed over 1 over infinity minus 4 over infinity cubed. Now get rid of the zeros. Okay, so I end up with 2. 3 over infinity squared is 0. 3 over infinity squared, yeah. 9 over infinity cubed is 0. Let's get rid of that so we don't think it's a minus sign. And then I end up with 1 over infinity, so that's 0. Minus 4 over infinity is 0. Uh-oh. Uh-oh. You see the problem? We ended up with a 0 in the denominator. We're going to get 2 over 0. And is this defined? Is that a number? What's that? That's nothing. That's infinity. That's undefined. That's crazy town. So when I get this happens, when I get 0 over 0, something over 0, this means the limit does not exist. Okay? I got to come up with a number here for it to be a limit. When I get something over 0, that means the limit does not exist. And in fact, you can give this answer, DNE, does not exist. Limit does not exist. Because we ended up with a 0, not a number down here. Okay? Let's try another one. X squared minus 3x plus 4 over x cubed minus 8. How's that? So for the vertical, I set the denominator equal to 0. Move the 8 to the other side. Take the cube root of both sides. And the cube root of 8 is 2. So this is going to have a vertical asymptote at x equals 2. For horizontal, I'm going to take the limit as x approaches infinity of x squared minus, that's an ugly 2. Let's just do that again. x squared minus 3x plus 4 over x cubed minus 8. Let's see, step 1 was divide by the biggest power of x. Okay, got it. X squared over x cubed minus 3x over x cubed plus 4 over x cubed, all over x cubed over x cubed minus 8. Now what do we do? Oh yeah, simplify. Okay, so x squared over x cubed is going to be 1 over x cubed. Let's put this over here because we're going to have a big divisor line. 3x over x cubed will be 3 over x squared. And this will stay the same, 4 over x cubed. And this is going to be 1 minus 8, right? Okay, well, I like that. Now we plug in infinity. So this will be 1 over infinity. I can't fit it there. 1 over infinity cubed minus 3 over infinity squared plus 4 over infinity cubed all over 1 minus 8 is minus 7. What's 1 over infinity going to be? Now we get rid of the zeros. 1 over infinity squared is 0. 3 over infinity squared is 0. 4 over infinity cubed is 0 over minus 7. What's this number? Is this a real number? Does it exist? Yeah, it's 0 over negative 7. That's just 0. So the horizontal asymptote occurs at y equals 0. So it's going to be some function. Well, here, let's do this. Let's go graph it. What do you say? So I go to Symbol Lab, and I'm going to graph it first, and then I'll share my screen because I got to look at it here. So I make a fraction, and an x squared, oops, x squared. Let me do this so you can see how I do this, because this is a really useful tool. Where am I? Oh yeah, right there. Share. Where are you? Symbol Lab. There you go. Okay, so this is. Oh yeah, I did that right. Fraction. Then I'm going to get x squared. Where'd my function go? There we go. Okay. X squared minus 3x plus 4 over x cubed minus 8. It's thinking. It's thinking. Oh, look at that. It's kind of a funny thing. So here we are at x equals 1, 2. Here's our vertical asymptote, which is what we found because we set the denominator equal to 0. And the horizontal asymptote, we found the curve slowly approaches 0 when we get out to infinity. No idea what's going on here, but it slowly approaches 0 when it goes out to a negative infinity. So that's what we found when we did our analysis here was, what is going on? How do I reset the zoom? I don't know. Okay, so there we go. That's gonna have to be good enough. Okay, so we ended up with this function here. Oops, I need to share. Don't know what's going on here. Let me shrink it a little bit. That didn't help at all. Okay, so this is what we found here, that we got a horizontal asymptote at x equals 0 and a vertical asymptote at x equals 2. Okay, so that is doing asymptotes. Let's go get a new sheet, and hopefully our Zoom problem is going to be solved. Doesn't look like it. Let's do another one. Uh-oh. Okay. So now, so we got the asymptotes, very important. Now let's talk about transformations. If I have a function, g of x is 1 over x, that's where we started, and I say here's 1, f of x is 1 over x plus 2. What is that? Well, this looks like f of x plus h, that we have a plus 2 grouped in with the x. And so this shows a shift opposite from the sign. So instead of a graph that looks like this and that, which is what 1 over x is, which was one of the 4 functions you need to be able to identify, it looks like it's shifted 2 units in the negative direction. So here's my vertical asymptote instead of being at 0. And there's no vertical translation, so no vertical shift. So f of x is this blue curve. It was shifted 2 units in the negative direction. Okay? Now, what if, oh wait, let's not do that. Let's do this. So what if it's h of x is 3 over 2x? Well, that, oh, no, that's not right. 3 over x plus 2. So this looks like 3 times 1 over x plus 2. And so this is still a -2 horizontal shift. But now, when you have a coefficient out front, this is also a vertical stretch of a factor of 3. So we pulled it 3 times bigger. So the function originally looked like this, because this is originally a 1 over x function. And now it goes 2 units over here, so our asymptote is there. And it's hard to show the shift because it's just going to get pulled up. So it's just taller. Kind of looks the same. Okay? You need to be able to identify what the shift is. Oh, so what if it's h of x is 3 over x plus 2 plus 4? So this is still a -2 horizontal shift. And this is still a vertical stretch of 3. But this is a vertical shift of 4. So my original function looks like this. And my asymptotes were on the x and the y-axis. But now I'm going to shift. So I'm going to shift -2. So that's where my vertical asymptote is, because when I put -2 in the denominator, it changes it to 0. And normally I would have a horizontal asymptote at 0, but I'm shifted up 4 units. So this is going to be my new horizontal asymptote. So my curve is going to look like that. And again, it's stretched by 3, but again, it's really hard to show that stretch because functions kind of look the same when they're stretched. So I can tell from this, by the structure of it, what the transformations are to the original function, which was 1 over x. This is basically a 1 over x function with a bunch of transformations on it. So now let's get to what I want to get to. Let's say we have g of x equals 3x minus 7 over x minus 2. And I want to show what the transformations are of this. I want to plot this thing. Well, it doesn't look like a 1 over x function. I'm telling you it is a 1 over x function, but it doesn't look like it to me. So we're going to have to do some division to try to get it to be there. And I'm going to first do synthetic. So I'm going to set x minus 2 equal to 0, x equals 2. So that's in the penalty box. And then I have 3 and negative 7, right? The 3 comes down, goes up here. 3 times 2 is 6. Add minus 1, remainder. Okay, so 3x minus 7 over x minus 2 is equal to 3 minus, here's my remainder, 1 over x minus 2. Aha! This looks like a 1 over x function. So there's a, let's write it so it makes a little more sense. Minus 1 times 1 over x minus 2 plus 3. That makes a little more sense. So x minus 2 is a plus 2 horizontal shift. Plus 3 is a same direction as the sign for y. Plus 3 vertical shift. And what's the minus sign out front mean? This means reflect. Let me write it a little neater. Reflection about the x, is that right? Yep, x axis. So if my original function is 1 over x, and it has its asymptotes here at 0 and 0, that's my original function. Oops, do it down here. Now I look at my new function, and there's going to be a plus 2 shift. So here's my vertical asymptote now. And there's a plus 3 shift. Here's my horizontal asymptote now. And so it would normally be like this and like that, but it's reflected around the x-axis. So really, I'm over here. Is that right? No, I think I'll be, instead of here and here, I'll be here and there, I think. Let's check. Let's think about that. It was over here at minus 2. No, I think it's like this. I think that's right. Do I get a picture? No, I don't get a picture. Well, let's go graph it. So let's stop sharing there. Do I still have, what you call it up? Where are you? Okay. Okay, so here is 1 over x. And then let's do, what did we get? 3 minus, I'm going to do it this way just because it's easier to type. 1 over x minus 2. Yeah. So here was our asymptote. Normally they would be here and here, but it got reflected around that asymptote and got put over here and here. It didn't reflect around the x-axis because there's no vertical asymptote over here at -2. So it got reflected around its asymptote line. Okay, so there you go. So is that all we need to know? We did vertical and horizontal asymptotes. End behavior is the same as horizontal asymptotes. We're going to stick with horizontal and vertical asymptotes and not look at funny things that have an end behavior. Let me show you. I'm sure you'll be thrilled to know that we're not going to do this. You could have a function that has an asymptote there, and an asymptote like this. So you could have a function that goes like this, that approaches this line and approaches here, and maybe goes like this, and then does something funny in the center. I've seen functions like this before. Really hard to figure out. So the end behavior here is the curve approaches some line. I don't think we're going to do those. Those are really hard to do. I don't think there's a lot of great payoff for doing that. So we're going to skip those in the homework problems, and it's important to reinforce, and I haven't really reinforced it yet, that if we don't do a problem type in the homework, you're not going to get it on a quiz or a test. The homework is like the quizzes and the test. If you ace the homework, you're going to do really well, okay? So you got to focus on the homework. So that's about it for chapter 2.6, horizontal and vertical asymptotes. Figure out what the translations are to a function. You'll probably in the homework have to look at a function and identify which graph represents the translations there. And so that takes some practice. I would recommend you look at the examples in the book because those will help a lot. Okay? This is a section 2.6 that gives students a lot of trouble. So you should stay focused on this. And if you have any questions, come ask for help. Because if you wait until the day before a quiz or a test, well, it's too late. You don't have any time to learn it and digest it. You needed to do that a week before. So don't wait until the test is looming or a quiz is on top of you to figure it out. You need to do it sooner rather than later. Okay? Okay, we will see.